Hello everyone. Today we will see our new topic called 1 dB compression point. 1 dB compression point plays a vital role in power amplifiers. Most of the linear amplifiers have fixed gain for specific frequency range. Now if you plot a graph between the output power and the input power, you will see a linear slope, a linear graph. The slope of this line is called the gain. As the input power continues to increase, so at certain point the gain will begin to decrease and the amplifier goes into a compression zone where no further output increase is possible. The gain gets flattened, meaning the amplifier gets into a saturation and its response becomes nonlinear and it will produce signal distortion, harmonics and intermodulation products. So for any amplifier, you should have high 1 dB power point. If you have 1 dB power point, if it is higher, then you will achieve higher linearity and that will give you better power amplifier. Now if you see the graph between the output power and the input power, you will see 4 different threshold point. POMDS is the minimum detectable output power. POMAS is nothing but maximum allowable signal. PIN-MDS is the minimum detectable input signal, and PAMAS is nothing but maximum allowable input signal. Now minimum detectable signal should be above this noise floor. So any signal has to cross this noise floor level to be detected. Now what is 1 dB compression point? It is the point at which your gain, the slope, is reduced by 1 dB. Now if you concentrate over here, there are two different slopes. This slope is nothing but this is theoretical slope and this is the actual practical slope of any transistor amplifier. Now from the theoretical slope, that is which is increasing linearly, if the gain is reduced by 1 dB, then we will achieve the point called as 1 dB compression point. And after which the slope gets flattened. Means if you increase the input signal, you will not achieve the same response from the output side. Now the next important thing is its dynamic range. Dynamic range is nothing but it is the range of the transistor where it behaves linearly. So it will, if you change the input, it will continuously increasing your output signal. So mathematically, this 1 dB compression point can be given as G 1 dB, that is gain at 1 dB is equal to the actual gain minus 1 dB point, that is 1 dB power. So gain is nothing but in terms of normal scale, it is output power upon input power. So gain at 1 dB will be power, output power at 1 dB divided by the input power at 1 dB. This is scalar value. Now if you convert this thing into a dB value, this division will become minus. That is now the output power in dBm minus the input power in dBm. Now this both the powers are nothing but it is present at 1 dB point. So output power at 1 dB point minus input power at 1 dB point. The dynamic range, we have already seen that it is a range of the output power during which the device behaves as a linear device. The dynamic range is generally very important characteristics of any power amplifier because it will identify the range of operation as well as the output power for a given input when the device is operated in class A mode, that is under linear region. Now if you see the mathematical way of writing dynamic range, so dynamic range can be given as, this is your actual dynamic range. So dynamic range is nothing but it is power at 1 dB, output power at 1 dB minus minimum detectable output power. This point, minimum detectable output power. So this is your dynamic range where minimum detectable output power, now this diagram I have taken it from my notes. Now if you see, this is the actual noise floor. The noise floor cannot be constant throughout. So some kind of deviation is there. So we need to consider that deviation as well. So the minimum detectable signal is given by the deviation in dB plus the noise floor value, that is N0 in dBm. N0 is output noise power. Now from the definition of noise figure, we have already seen that noise figure is given by signal to noise ratio at the input divided by signal to noise ratio at the output. So signal to noise ratio at the input upon signal to noise ratio at the output. If you simplify this equation, you will get SI upon SO multiplied by NO upon NI, where SI upon SO can be written as 1 upon G and NO upon NI as it is. Now from this equation, you will try to find out this NO. So NO will become F into G into NI, where NI is the input noise, which is nothing but the thermal noise given by K T0B, where K is Boltzmann constant, T0 is the ambient temperature and B is the bandwidth. Now let us try to solve one of the problem based on 1 dB compression point or a dynamic range. So this problem I have taken it from the reference book. The question is a high power broadband amplifier with a bandwidth of 8 GHz, a gain of 20 dB, noise figure of 7 dB can produce a power of 30 dBm at 1 dB gain compression point. What is the dynamic range? Assume T is equal to 290 degree Kelvin and X is equal to 3 dB. So here we need to find dynamic range. So data which are given, we'll first put down that data. Okay, now to calculate the value of dynamic range, we should have the noise power as well as minimum detectable power, output power. So for the output noise power, we have already derived this equation. The output noise power is equal to F into G multiplied by Ni. Ni is the input noise which is given by KT0B. So if you substitute all the different values which are given in the question, you will get your NO is equal to 1.6 into 10 raised to minus 8 watts. Now to convert that thing into dBm, you have to take 10 log the scalar value of the noise divided by 1 milliwatt to get your power in dBm. So step 2, you will try to get your minimum detectable signal, which is given by X plus N0. N0 we have already calculated, output noise power. X is given 3 dB. So you will get your minimum detectable signal as minus 44.95 dBm. And the last step, you will try to get your dynamic range. Dynamic range is given by power, output power at 1 dB minus minimum detectable output power. So dynamic range comes out to be 74.95. That's all for today. Thank you.